Well, we have more people coming. Yes, they just landed. Let me wait a couple more minutes, okay? And before we start, I just want to tell you thank you very much for this coming to this class today. And I have I will say the greatest honor and the happiness that you can not imagine that today we have a guest lecturer. And today I have the pleasure of having my colleague and friend, Dr. Jose Luis Rueda. And Dr. Jose Luis Rueda is a associate professor at the Technical University of Delft in Delft, Netherlands. And he has been a very positive and very engaging collaborator of mine for quite a while. And just for a very short introduction, he is electrical engineer from South America, from Escuela Politécnica Nacional, National Polytechnic School in Quito, Ecuador, and he is cum laude in 2004. And also he has been a master and PhD from, oh Jesus, this is, okay, yes. In 2005, he was awarded the 4-year scholarship for the German Academic Exchange Service, and also for the PhD student at the Institute of Electrical Energy, National University of San Juan, Argentina. Between 2007 and 2008, he was a guest researcher in the Institute of Electrical Power System at the University of Duisburg-Essen in Germany, and it was supported by the German Academic Exchange Service for a short-term scholarship. In November 2009, he received the PhD degree in electrical engineering from the National University of San Juan, and he obtained the highest score that you can get over there. In Spanish is sobresaliente, outstanding. Between 2010 and 2014, he worked as postdoc at the Institute of Electrical Power System at the University of Duisburg-Essen, and where he got the habilitation qualification for postdoctoral degree. 2014, he started as associate professor at Technical University of Delft. He got the tenure in 2017 for the Intelligent Electrical Power Grid at the Department of Electrical Sustainable Energy at Technical University of Delft. In 2018, he was promoted to associate professor, and he has a very extensive experience in research and delivering successful projects. Also, he is the chairman of the working group in modern heuristic optimization. Also, he is vice chair of the same working group of the modern heuristic optimization, and he has been involved in several journals as associate editor. And also, there are some details. He has successfully completed several of European projects, and of course he has a long track of publications. Some of them I have the joy to be with him, several books about the excellent PowerFactory. And for that reason, today is extreme pleasure having Jose Luis, and today he will be talking about small signal stability, eigenvalue analysis, and so on. Jose Luis, if you are around, please take the floor. The floor is all yours.
Thank you, Francisco, for that kind introduction. I hope everyone can hear me very well.
Yes.
Okay, thank you. So I will just now prepare my presentation for screen sharing. And here I think you have to stop sharing first, Francisco, and
yes.
then I can.
Yes, sorry. Now
Thank
it's all
you.
yours.
Thank you very much. And then I will share mine. I think this should be much better now.
Yes, it is.
Let's see. You can probably also see me. I also shared the video now. So welcome. First, once again, thank you very much, Francisco, for inviting me to give this guest lecture to your students. I'm most delighted to cooperate with you and to share our energy, our passion in helping our young engineers to explore these adventurous fields, so the dynamics of power systems. Well, today I will talk about some basic notions of the small signal or a small disturbance, the rotor angle stability. That means when we apply gradual changes like a load steps, like 10% increase or decrease of load, for instance, of a change in a type position. So what happens with the dynamic performance of the system as excited by this behavior? And usually, because of the size of the disturbance, this phenomena, the nonlinear behavioral rotor angle, can be approximated by some linearized model. So it is all about the use of linearization technique to get some insight on the dynamics of the rotor angle of the synchronous generators. So the angle stability is by default the ability of synchronous generators to remain in synchronism after any type of disturbance, both large or small size. In this case, of small size, we can apply these techniques of linear systems, basically, either by taking the whole differential algebraic equation system model and linearizing it around some equilibrium point in the previous disturbance condition, or by processing the time response and fitting some linear model like a Fourier series or something to the measurements or simulated data. So today we are focusing on the differential algebraic equation system and its linearization, and how we can use this to get some insight on the dynamics of the system by using this technique. So this is all about today. And then in the part one, we are going to explore the fundamentals behind this approximation, so the linearization of the system, to analyze the dynamics of the rotor angle, excited by small disturbances. And in the last part, well, we have just two parts. In the second part, we are going to extend these fundamentals to reflect a bit on how we can use these for analysis and design of damping control. Damping is about decreasing the amplitude of the oscillation. So the overall problem of rotor angular stability is that if they increase too much uncontrollably, then the protection devices of the synchronous generators will kick in the out-of-state protection, and they can be disconnected. And if this is part of some sort of cascading outage, then we have a fast deterioration of the performance and progressively something that is in the server, that splitting of the system into small islands, and even much worse, blackouts. So we would like to always have well-damped oscillations irrespectively of the frequency range. So damping control is about the rate of decay. So let's start with the first part, the fundamentals. I have some slides. Some of them I will state just shortly. I did some illustrations based on the software Deflt PowerFactory, a tool that is used very often by Professor Francisco Gonzalez-Longatt in many works concerning education and research. So in order to align also with that spirit, we have examples here based on that tool. Sometimes I will just stop quickly to say how to use some functions, and you can read it in the slides because it's more or less prepared to be intuitive to discover how to use them. And what they will just try to highlight is what we can get with the function. So as I was saying in the beginning, there are two ways to analyze the behavior of a small signal stability or the rotor dynamics in the so-called small signal. That means when a small disturbance is applied, we have techniques that can be used from a model-based point of view. So we have the differential equation system, and we do something with that. And in the second case, we have data that can come from simulated conditions or measurement fields, signal records. In the first type, then we are basically taking the differential equation system and linearizing in around the equilibrium point to determine the characteristics of oscillation frequencies, the frequencies and damping ratios, and what are the main components involved in those oscillations. So that's all the information that we get in a nutshell. In the second case, we can get some information, but this is more limited because we are talking about just taking specific portions of data in specific locations. And sometimes it happens that we are lucky to measure the dynamics that have been properly excited, and we can get good information of what is the oscillation frequency, the damping ratio, the phase displacement, and so on. When we fit a linear model like a Fourier series, for instance, or a discretized form like in the Brownian analysis. But sometimes if we take this portion of data in a location in which the oscillatory behavior is not so highly excited, then we might get just some numerical estimations, but they are not really reflecting the dynamics of the oscillation. So this is quite some topic. Maybe in a subsequent lecture, we can go into all details of how this works. So today we work mainly on the upper part, in which we take a differential algebraic equation system, and basically we need to get this representation that we see here in the equation with a set of differential algebraic equations. On the upper part, analyzing the variations over time, the time derivatives approximated by a small signal approach, as a function of the state variables and the input variables of the system. And if we put some meters to monitor that, we have the so-called output variables as a function of the state variables and the input variables. And these matrices A, B, C, D, they are related inputs or state variables with either the derivative or the measurement where we are placing to observe the system. The other one is fitting a mathematical model, as we have here, some kind of damped sinusoidal or exponentially damped sinusoid to try to estimate the information of the oscillations from the system. So let's focus on the first part, as is in this lecture. So normally the nonlinear dynamic behavior of any power system is described by these equations 1 and 2, in which we have a differential part reflecting the time derivatives or the derivatives of state variables, with respect to the time, and as a function of the state variables or input variables, if we define something that will be also modulating the behavior on a time-dependent basis. Then we have also the output variables. So we have the other set of nonlinear functions, both as this also is a function of the state variables and the inputs that we might define. Example input will be, for instance, if we add some signal to modulate the reference of an excitation system, for instance, right? Or the state variable could be, for instance, the state of time delay of an exciter of a governor, for instance, or could be also associated to a washout filter, right? These are examples of state variables. Could also be, in case of synchronous generators, the variation of the fluxes in the windings of the stator or the rotor, right? Then this is a nonlinear set of equations, and we have a number of equations associated to the different devices. So, for instance, you probably have seen some material about modeling of synchronous generator. You might recall that in the most detailed form, a synchronous generator might be modeled with up to 9 state variables, comprising all fluxes in the windings. Also, the rotor dynamics, we have 2 variables of this, the variation of rotor speed, the variation of rotor angle. And then we can increase this model if we include controllers by at least 2 or 3 variables. If we add the exciter, or 2 or 3 more if we add governor, and other 2 or 3 we add the stabilizer, depending on how big is the model, the control diagram we add. So in a nutshell, we may end up with something that is between like 10 or 15 or something like that. Per generator will include the controllers, and then we have depending on the number of units we model like that, so that will be the size of the system in terms of these equations. So mathematically speaking, this is a quite complex system to solve, because we'll have to integrate all these derivatives and also the associated algebraic equations for the measurement points we're going to define to observe this dynamics. So which will be very difficult to define and to translate into simple metrics that just tell us what are the oscillatory frequencies and what are the damping ratios of the most critical oscillations that could be excited whenever a disturbance is applied in a system. Because we are applying a small disturbance, as we say in the beginning, we can use this linearized form in equations 3 and 4. As we see to the right, we have just applied a small perturbation to the differential equations to the left, and then we have some approximation of the derivatives, right, as a function of the state variables and also the inputs, and something similar for the outputs. These matrices A, B, C, D are called the Jacobians of the system, because they are more or less the derivatives of these functions f and g of the nonlinear model original in equations 1 and 2 with respect to the state variables or to the inputs, as we see here. Something similar for the functions g for the output variables. The most interesting matrix in these formulations of equations 3 and 4 for the quantitative assessment of the small signal stability or the rotor angle stability under the small disturbances is the matrix A, which is often referred to as the state matrix or plant matrix of the system. Why is that matrix so important? Because the eigenvalues of this matrix will give us this qualitative assessment of the oscillations. So what are the most critical oscillations, aperiodic or sinusoidal, and what are the damping factors? And then we can get some additional information that we will see in the next slides to identify the main related components. So from the matrix, we can compute the eigenvalues, and from linear algebra, you might probably recall that matrices can have real eigenvalues and complex eigenvalues. In the case of complex eigenvalues, they come in complex conjugates, as we see in the middle, right? And for the case of real eigenvalues, as we see here in the equation 9 to the very left, we would try to imagine what does this real eigenvalue mean in the nonlinear response of the system in the small signal. For the null perturbation is basically exponential term that will have this real part as a factor that scales the time parameter, right? So this will be a non-oscillatory mode. For the case of complex conjugates, because they come in complex in a pair, so we have here application of the Euler identity, and we will pay attention to the rightmost part of the equation 10. Basically, then we will mean in the time response of our signal, where we are measuring the rotor angle the performance as reflected in that signal, we will have exponentially amplified or modulated the sinus or cosinus reference waveform. And this omega will be the oscillatory frequency of the oscillation, and the real part of the complex conjugate will be the rate of decay. And from these two, as we see in equation 12, we can define the so-called damping ratio of the mode. We will give some interpretation to this in the next slide. So basically, for real eigenvalues, we'll have the aperiodic or exponentially growing or decaying oscillations. And for complex conjugates, we have some exponentially modulated sinus or cosinus reference signal. And this means we have an oscillation with a given angular frequency, and then we have the damping ratio of the oscillation. So let's move forward. Now let's visualize all these in the complex plane, because these are in the complex variable. We have an imaginary axis that is j omega for the imaginary part, and a real axis, which is the real part. And then, for instance, depending on the location of the eigenvalues in the complex plane, for instance, we see that for the real value only, if it is a positive one, will be to the right hand side of the complex, meaning on a periodic drift. It will be on the left hand side, will be on a periodic decay, right? And then for the complex conjugates, for the right hand side will be a growing oscillation. For the left hand side, it depends. If there is to the left of some damping threshold, will be some oscillation that will tend to decay with a number of cycles depending on the damping factor. If it is below that, it will be a slowly decaying oscillation until the point that if the oscillation is oscillatory mode is located on the vertical axis, this means we don't have real parts, so we don't have any damping in the system. So it will be a sustained oscillation. This is what we will observe in the time responses that we are going to check. We have here more or less a definition of the units for each of these quantities. So this is for the eigenvalues of the state matrix. And for linear algebra, you probably also recall that when we get the eigenvalues of a matrix, we can also get the eigenvectors. And each eigenvalue of a matrix will have an associated right eigenvector and associated left eigenvector, right? And how we use that in linear algebra is basically by using these matrices of eigenvectors and the eigenvalues, we can operate the original matrix to make it diagonal, for instance, right? To transform it into another type of representation. So these eigenvectors that are mathematical artifacts for some transformation in linear algebra, they are using in small signal stability to try to extract some knowledge from the oscillation, because so far, for what we can see from these eigenvalues, we can only know if this is growing or decaying, is a periodic or sinusoidal, and that's it, right? But we would like to learn more. So what the units are oscillating, for instance, what the state variables of those components are the most heavily involved or influenced in this oscillation. So this is why we use the eigenvectors right and left, and also there's a byproduct by this with the multiplication of the right and left, which is called participation factor. So we have also participation vector, and this will be some adimensional measure to more or less weight on average the sensitivity of an eigenvalue with respect to a given variable of the system. So that is more or less in a nutshell why we need this. So let's go a bit over the details. This is more or less that for each eigenvalue, we will have, as we can see here, when we do the calculations in any software like MATLAB or PowerFactory, we'll get a matrix of eigenvectors, each one sorted out in the order of the eigenvalues that have been computed by the algorithm, right? So we have a lambda 1, lambda 2, and lambda n. The eigenvectors in the matrix will follow that order. And the elements of these vectors, column-wise in this case, correspond with the order of the state variables that your software tool has defined. Often happens that most of software tools, for instance, first place all state variables of synchronous generators like fluxes and rotor angles, and then all the controllers. And then once a full machine with controllers is done, then the next block will be the block of state variables of the other generator, and then maybe some voltage source converter related variables, and maybe some motor variables. So it depends how the software defines internally how to sort the equations. But this order defines more or less or corresponds with the sequence of the elements of the eigenvectors, or in other words, the entries of the elements of the eigenvectors. So we'll have to check in your tool how these equations are sorted to understand what is the meaning of each element column-wise here in the eigenvector. And then in terms of the association to eigenvalues, this depends on the algorithm, because basically what happens is in the software tool you use will take some starting points in the complex plane, and will start complex space start to iterate to find these elements, and by this iterative process, this order of the eigenvalues might differ. We implement the same algorithm, or when you use the same algorithm in different tools, right? So what could differ is the order of the columns. when you do the calculation of this in one step or another, what will not differ is the order of the elements column-wise, because this is how the linear tool that created the matrix has worked with. So this is, in a nutshell, what is the right eigenvector, and we use it often in small signal instability to analyze the extent of excitation of an oscillation as observed in some given variables that are listed or sorted or placed here in the right eigenvector. So for instance, we have here an example in a right eigenvector in which we extract only the elements that correspond with the dynamics of the rotor speed, so the state variable or rotor speed. So in this example, I took maybe this is an element of 50 variables, a small system, and only 4 of them are 4 generators in this ideal example, but just took these 4 elements that are from these entries. And these are always complex numbers. And then with this, I can do some examination. So for instance, I can plot them in the complex plane. And the way we observe it is also correlated with the way we see the angular displacements here when we look up the argument of this complex number. So in a nutshell, the right eigenvectors is helping us to more or less infer the oscillation type. So if there are generators that will tend to cluster, they might oscillate with somewhat different relative amplitudes, but the most important here is the phase. So if they are in antiphase, we're talking about generators oscillating against each other. In this example, we have G3 and G4 oscillating against G1 and G2. So we just take the elements of the eigenvector to try to see the oscillation type by looking at whether they are in an antiphase or not. And an antiphase or no means usually the phase difference should be larger than 90 degrees, or in other words, closer to 180, closer to antiphase. Normally, it's not that perfect. Can be 120 or 110. And the reason for this not perfect antiphase is because we have some capacitor or inductive elements that are modulating or changing the angle between voltages and currents across the network. So this changes this and makes it not to be perfectly in antiphase. So this is for the right eigenvector. For the left eigenvector is something similar. We also get a matrix. In this case, it's a row vector. So row-wise, there is an association with each eigenvalue, and the elements of this in each row are associated to the state equations as defined by the software tool, how it was sorted there. So we take loss one of the eigenvectors here. In this case, we make a transpose just to have it to observe it column-wise like the right one, but normally it is row-wise. So the entries of this vector also have an order corresponding with the order of the differential equations that your software has defined by default. These left eigenvectors are not per se used to extract some conclusive information about the oscillation. However, they can be taken as a very, especially the magnitude, as a very qualitative metric to more or less say, what if I apply a control signal del to modulate, to which extent I am going to cause a movement in the eigenvalue in the complex plane. However, this is valid only when the system is excited by the initial conditions, so by the power flow conditions before the disturbance happens. Right? Once you have a disturbance, then other factors influence, and then we cannot say that. For concluding the degree of excitation or influence in an oscillation by adding an input control signal, we need to have a more complete measure, which means we use partly this left eigenvector, and we also need to define, you recall the matrices, the matrix that relate the state variable with an input that it might define. And from this, we need to take some geometrical metrics, and then we can quantify the sensitivities of the oscillation modes in the plane with an input signal. That is a more complex, and we will come back on this in the damping control. So, however, sometimes it's taken as a proxy. A proxy means as a very approximating factor to judge a bit the degree of excitation. But in this case, only applies when we have the initial conditions from the load flow calculation. And lastly, we have also the participation factors, which are calculated by multiplying left and right eigenvectors associated to a given eigenvalue. So we have here the formula, and their interpretation is that they measure the sensitivity, so the derivative of the real value or complex conjugate value, the eigenvalue, with respect to an element of the state matrix that could be associated to a controller, for instance, like the time constants or the gains of exciter, for instance, or some other adjustable parameters in a power electronic converter or a machine. And then this is computed by multiplying the elements of the left and the right eigenvector. For the case of the right eigenvector is the kth entry of the vector associated to that eigenvalue. I is it means the eigenvalue number. And then we take it from the row, kth row from the matrix and the ith column of this matrix of right eigenvector. And then for the left eigenvector, we take the ith row and the kth column. So we take correspondingly for a given state variable, basically, k, and for a given eigenvalue, I, the elements that are corresponding for this in the eigenvalue in the left and right eigenvectors associated to the given eigenvalue of interest. So this is an adimensional measure, and also we have per eigenvalue then a participation vector if we do all these multiplications left and right, and then we have a participation vector associated to each state variable, basically, and then we can put all these vectors all together to build the participation matrix. And then what the research so far has shown mostly is that this will be, by the way, these elements here of the equation 18, each entry of the vector will be a complex number, but normally what has been widely used is only the magnitude of that complex number, as we see here in this example, when we took the participation vector for a given critical eigenvalue, and from that we took only the entries for selected variables of interest, like the rotor speed deviation, following the example of the right eigenvectors. From this, we can see that the magnitude of these vectors will tell us a bit the degree of participation of these, in this case, of these generators in the oscillation. So, for instance, we see that generator 4 will have the highest participation. Generator 3 will be also the second highest. So they are the most heavily involved in the oscillations. And 1 and 2, as we saw in the example of the right eigenvectors, they are in antiphase with 3 and 4. However, if we would like to do some control action, the best locations will be G4, of course, which is the most effective one, G3 the second one, and maybe as a third option, G1. G2 will be not so effective because it's almost insensitive to any control action that they might perform there. So it might have some stabilizers in these generators, especially 3 and 4, if we like to increase the damping of the oscillation. Here it's well to recall that we have a value of 1, because basically these 4 values were taken out and then they were just scaled out to or divided by the magnitude of the highest among the value among them. That's why normally it is not 1, but however the conclusions will be similar. To finalize this part, there are different methods that are applied in different tools like MATLAB or PowerFactory. One method is the QR method, which computes all eigenvalues of the systems, and this can be used for power systems with up to 800 states. So maybe we say we model a machine with controllers with around 10 state variables, so we have 80 machines, for instance, in the system. And all models, all oscillatory modes that, or periodic modes that can be excited in the system will be calculated completely by these methods. There's another alternative to this is the QSET method, which is another iterative method basically to compute the eigenvalues. For systems with higher number of state variables, like for instance the European system, we have hundreds of, almost thousands of machines, and we say even if it's 510 variables will be 5,000 variables. That is impossible to calculate with QR or QSET methods. So for that, the usual approach is to put some guess in the complex plane and iterate around that, hoping that we find the critical eigenvalues around that region. And that kind of methods are called selective methods, because we try to focus the search in a region of the complex plane, and then we will try to search around that, and we will get only a bunch of methods, a pocket, a small amount of eigenvalues that are located around that specific location. There are different types of algorithms, by the way. This research challenge there has been always how to make it in a computationally efficient manner. So with a few iterations to find the most critical eigenvalues and with a very high degree of confidence. That has been a matter of research for almost 30 years, like between the 60s and the 90s, more or less. And we have a number of families of methods that could be used for that. One of these is the Arnoldi algorithms, which is the most commonly used in most open source and commercial tools, which will do these iterations over the space. And this is in principle applicable to systems of any size, because if we have a system with 10,000 variable states, for instance, or 10,000 eigenvalues, theoretically, we might only get 1, 2, or 3 maximum, not all 10,000. So this is what we can expect from this kind of selected method. That's why it's selected. We just want the most critical ones. And this will be effective only for a few of them, maybe 1, 2, 3. Well, we cannot say we can get 10 or 20 eigenvalues. That we can get theoretically as an outcome, but this will be just numerical artifacts. So a lot of good care should be taken with selecting these methods and with the configuration to see how to find the eigenvalues and whether these outcomes are trustworthy. So this is a comparison, more or less, if you would like to see if there is a match between the selective eigenvalue calculation or partial eigenvalue calculation and full eigenvalue calculation. So we have here, for a small system, we see when the partial eigenvalue calculation is correctly set, it will match with the findings only for the critical ones. In this case, these are the critical ones because, as we saw previously, eigenvalues close to the imaginary axis means sustained or poorly damped oscillations. So these are the most critical for a small signal for the rotor angular stability. So you have tuned your selective algorithm. In this case, we have the implicitly restart unlearning method, which is available in PowerFactory, for instance. In MATLAB, we will get this good match, meaning that we have customized well the Arnoldi method to do the selective or partial eigenvalue calculation. This other figure illustrates very nicely the more or less the computing effort that in CPU time with a single core unit. It will try to estimate the eigenvalues for the state metrics of this system of different sizes, for instance, from system, again, if we idealize a system with 10 generators, this was with 10 state variables, will be from the 10 machines to 100 machines, for instance, right? And then we'll see how the complexity, the CPU time grows for both types of algorithms, the full eigenvalue calculation and the partial eigenvalue calculation. However, for the full eigenvalue calculation, the computation type grows dramatically after around 600 to 800, which more or less is the limit. So especially if you would like to repeat the calculation of the linearized model for different operating conditions, like for different types of highly loaded condition versus lowly loaded condition, I want to make something more fancy, like 100 loading scenarios or 1,000 or 100,000, this will become really prohibitive because you will have to wait several hours or even days to get your results. So that's why, but in those cases for very large systems that are larger than 800, it's better to go for a selective approach. Before that, you should make sure, like we see if you're to the left, that your calculations are trustworthy. Just be careful with that. So I have now, so just some examples how to do these calculations in MATLAB. I don't know, we can make some quick questions now, 1 or 2, or we leave it to till the end. Yeah. Okay, maybe we can do one question at least or two now. If there's any question, please. Okay. We have still some time left, so you can make more in the subsequent slides. So we'll move now. We just with some basic examples in PowerFactory. We have covered the theory of this more or less. So there's a useful function in MATLAB called it EIG, and the input of this function is the state matrix that you get, for instance, from PowerFactory or from another open source or accessible tool or package done in MATLAB, like Power System Toolbooks or Power System Analysis Toolbook, PSAT, and there are many, MathDin, they are different. You pass the state matrix, and then you will get the matrix of right eigenvectors, a diagonal matrix with the eigenvalues being the elements of the diagonal. So each element of the diagonal will be having associated a corresponding right eigenvector column-wise here in the matrix phi. And the other matrix is the matrix of left eigenvector. They are non-normalized. Non-normalized means that there is no correspondence between the right eigenvectors and the inverse of the left eigenvectors. So they are not orthogonal. Yeah. Then we have another command for the case of the selective or partial eigenvalue calculation. This is EIGS. S means sparse or selective. Yeah. And then you also pass through this function the matrix, the state matrix you get from the software you have applied, and you get the right eigenvector matrix of right eigenvectors and a diagonal matrix with the elements being the eigenvalues of the system. So you also have these calculations in MATLAB, in PowerFactory, like from 2016, you see some icons like this, more or less. And then you have to select the function of modal or eigenvalue analysis. You can configure to select the QR or QSET method that I said before, or Arnoldi method, selective method. When you select the Arnoldi method, you will have to input the starting point for the search in the complex plane. That means the real and imaginary part of the point around which you are going to search critical eigenvalues. That's it. Then you can configure some advanced options to make the software to output you the left eigenvectors, the right eigenvectors, and participation factors. In PowerFactory, they call controllability for left eigenvectors. However, as I told you before, controllability is something that involves not only left eigenvectors, but also the input matrix. And observability, strictly speaking, is something that involves the right eigenvectors or the output matrix. So be careful with this. This is just an indication of the software to tell you that can be used for these purposes of analysis, controllability, observability, but however, these elements alone are not controllability or observability measure, are just for qualitative analysis, as I said before. Then you can also output this to MATLAB files if you want. You see, you can get MATLAB files, and you can also output to text files in a directory that you might choose. All right, so then this is more or less how you will visualize in PowerFactory all the oscillation modes. In these examples, we see there are complex eigenvalues in positions 14 and 15 in these sorted list of eigenvalues, which have a frequency around 0.5 hertz, which is typically an inter-area oscillation. The damping ratio is relatively low, is 4%. So normally, the damping limits, damping related limit of a system is depending on the characteristics of which system. Some systems are very strict, like 10-15%, especially systems with the very long transmission lines spanning over very long regions, like in Argentina or US, for instance, or Brazil. Others are a bit more relaxed, around 5%. This is more in heavily meshed systems in which with something like 5% will be enough to damp up good oscillations. So then these are suspicious eigenvalues to be critical or interior oscillations with a very low damping ratio. This is our toy system in this example, and then we can get the matrix of the system, and then we can import it in MATLAB with this command here, and we can get the eigenvalues calculated in MATLAB, and they will match more or less with what we have here in PowerFactory. And this is what we do in the example. You see we have more or less similar oscillation frequency for the critical eigenvalue and similar damping factor. However, the order, it differs a bit because the algorithm QR in MATLAB might have a different way of sorting the eigenvalues. But this is because of the way the iterative the iteration in the complex space, in the vector space is done. So and then we are going to plot them with these commas in MATLAB, for instance, and we can plot also with this S-grid comma the lines of the damping thresholds. So we see more or less that there is some poorly damped oscillation below 5%. This is our damping limit. And there are curiously two modes that are located at the origin. And these are called the zero eigenvalues, which are usually a consequence of two things. We have a lack of units of absolute rotor angle, not defined in our model, or we have ignore the damping constant of the machine. So all the generator torques are independent of the speed deviation. Okay. So when these two things happen, we have at least two eigenvalues on the complex plane, not meaning that the system is unstable, but it's just a consequence of these modeling aspects that have been neglected in our system. And then we can do some similar plot to see the damping lines here in MATLAB, in PowerFactory as well, by clicking on this icon we have here to plot, do some plots, and then we select the eigenvalue plot, and then we get something like that. We can also do some simulation to observe and then feed a mathematical model. And if we feed it here, we should get something around 0.5 hertz and 4% damping ratio, more or less. PowerFactory would output the order of the state variables. That is what I told you in a TXT5 called variable to IDX underscore AMAT. And as you can see here, they have sorted out the synchronous generators 1, 2, 3, 4 in a given order for the corresponding state variables. So this psi means the fluxes, and then we have in the stator, in the field, two damping windings, and then we have rotor speeds, and then we have rotor angles. So we have 6 state variables for these generators for each of them. So we have 24 because we have 4 generators in the system. And this is how they have been sorted out. And with this indexing, we will have also the elements, the order of the elements in the right eigenvectors and in the left eigenvectors and in the participation factor. So this order will be kept. Even if you export the matrix A to analysis in MATLAB, for analysis MATLAB, you will keep this order. What will differ is the order of the eigenvalues because of the iteration. But the elements of the eigenvectors will always correspond with this sequence. So let's take, for instance, the speed elements. That means the indexes 5, 11, 17, and 23. We will do this to check eigenvectors and participation factors. So we just took these indexes, and then we can do a compass plot of the right eigenvector for the mode 13, which was one suspicious of inter area. And we do it for all the elements that we have there of this speed entry 1, 2, 3, 4. So the element 5th, 11th, 17th, and 23rd of this matrix of variables. And then we get the compass plot, and indeed we have generators G1 and G2 oscillating in antiphase with G3 and G4. So this is an inter area oscillation. Very likely. Now, the last thing we need to know is the extent of participation, and for that we need to look at the participation factor. We can do the same plot, compass plot in PowerFactory. For that we use this function mode phasor plot. We select the eigenvalue, you see, and we select the right eigenvector to plot, and then we can even select the rotor speed variables by clicking on this icon. You see, like this. We select the eigenvalue, we select the variables to monitor the speeds, and then we get the compass plots. This is more or less similar like what we did previously in MATLAB. Lastly, we do the participation factors. So we take in MATLAB, we invert to calculate the left eigenvectors. I invert the matrix of right eigenvectors to make the orthogonal, and then I will take the speed entries for the eigenvalue 13 or 14, and I can create a bar plot. And these were the speed entries of the generators, and you see generators 3 and 4 are the most heavily involved in this oscillation. And then the generator 3 is especially a good candidate for addition of power system stabilizers to increase the damping of the oscillation. You want to make it higher than 4% or 0.04. We can also do this bar plot in PowerFactory. We go to the function mode bar plot. We select the eigenvalue. We select the participation vector. We also select the element we want to monitor, the state variables. We can select the rotor speed. This is the example how I selected the rotor speed. For instance, you just click on each of them and they are selected or shortlisted. And then after finishing this and executing here, okay, in the bar plots, you will get the bar plots. It's just more or less rotated 90 degrees compared to the one in MATLAB. However, the conclusions are the same. Generator 3 is the most dominant. And it's good for participation, for addition of power system stabilizer. So this was more or less an example of how we can use these tools, PowerFactory and MATLAB, to compute the eigenvalues and to get some more insight into the dominant variables and involved with the units in the oscillation, which is all what we need to characterize the electromechanical oscillations in any system. I will finalize this presentation with a very short overview of how we can apply this knowledge for damping control. Well, how we use these metrics, the eigenvalues or participation vectors and participation factors in damping control. This is the last thing we need to learn today, as promised at the beginning. Before doing that, let me just say a few words about the stabilizer, which is a control loop supplementary. It's an additional control loop that is usually superimposed on the reference. So the output signal of this controller is superimposed on the reference of the governor, of the excitation system. And then the input of this controller can be a variable that might be more effective for the given system than others. It could be the rotor speed measured locally of the machine, could be the electrical power or the acceleration power. Acceleration is electrical minus mechanical, right? And or the measured frequency at the terminals of the machine. So normally the rotor speed is the most widely used and most effective signal for oscillation damping. And then this passes through some number of blocks. First, we have the washout, which is more or less is used as a high-pass filter to prevent steady-state changes when there is no intervention needed from this supplementary loop. Usually, you have time constants around 5 to 10 seconds. Right? And then we have lead lag compensation to compensate for the phase lag between the exciter input and the generator electrical torque. So we have to tune this time constants T1, T2, T4 to compensate for this phase lag. That can be done with classical control techniques like the Nyquist, Bode, or root locus. If we reduce the system to something like a single machine infinite bus, or we can formalize it as an optimization problem and solve it for many variables if we have many stabilizers in many machines. A more multivariable and complex problem. And lastly, we have the gain, which will define the amount of damping that is introduced by the stabilizer in a given frequency, the spectrum defined by this lead lag compensation. And then we have to carefully determine this, how high it should be. Of course, 0 means no damping. Well, as high as possible. Of course, it should be more beneficial for a system, but there will be a point in which, after which you increase this gain, there will be no effective improvement in the damping. So this has also to be tuned depending on the frequency response of the system. But then you have these limits, which we have an upper and lower to prevent the high level of contribution in the case of higher limit during large oscillations. And the other one, the lower one, is to have a good margin for control action over a number of conditions. So the tuning problem of this kind of stabilizing feedback loops I told you is aiming at determine the values of these time constants of the lead lag filters and the gain. And this can be formulated as an optimization problem. I won't say too much here or nothing at all about the classical methods like root locus, Nyquist, or Bode diagrams, because this will be more for single machine infinite bus. I would prefer to focus on the multi-machine aspect, which is the most complex. And then actually these formulations are applicable for any type of systems, which also includes lots of renewables. So the tune problem is an optimization, but when we talk about optimization, that can be different types of formulation. We need to define objective function and constraints, basically, but this depends what we want to tune and what we want to achieve. This is an example of objective function. We want to, for instance, minimize the difference of the least or the damping ratio of the least damping mode in the system among all critical modes versus the threshold that we define for damping, and we just square the difference to make sure that when it becomes null, we have reached, we should stop optimization. And we can add also the difference between the real part of the most critical mode with the threshold for the real part of the system. And we could weight this to give some more importance, whether we prefer first to make it more exponentially decaying, and then make it focus more on the cycles, reduce the number of cycles of the oscillation to decay. This is an example of a choice that could be done. And this is how to calculate the worst damping ratio and the worst real part across different oscillatory modes and for a number of operating conditions in the system. So this is most detailed formulation. And this is subject to a search space defined by the range of the parameters that we're going to optimize. So for instance, we could say, I will try to tune the gains to be somewhere between 1 and 100. So the optimization will tell me what is the best value for each of the gains, for each stabilizer in the system. And we define also some lower and upper limit for the times constants of the dead-like filters. The consequence of this tuning is that once we have successfully optimized, we'll have eigenvalues that will all confine to the right or to the left, sorry, of let's call it D-shaped region, because the one part is defined by the real parts we define on the right element of the equation 20, and the other is this diagonal shape or this slope here by the damping threshold. We are confined. The only risk that might happen is that maybe one oscillation mode will be just in the corner here, which might be sensitive in the sense that if some change occurs in the system in a condition that was not contemplated in the design, this might become outside this region and will become poorly damped. And this might be a mode or relative high frequency. We may have some subsynchronous or supersynchronous oscillation that might be dangerous for our system. Right? So this will be one problem. Another objective function that we could think was just minimizing the real part. In this case, we are just confining to the real part. In this case, we might have even this problem more complicated because you have most going to the threshold, and if there's some operating condition that was not considered here, we might go to the left, and then we'll have even one or more poorly damped oscillations of higher frequency, which is also not desired in any system. So one thing to try to mitigate this problem is to try to introduce an inequality constraining optimization. That means we would like to make the optimization search to ensure that the delta of the frequency of the modes that they are tuning moving on the plane will not be higher than a desired threshold. So not to make it go high, right? Or not, okay? So that will be one possible option in optimization. If we do it only with the damping ratio, then we'll go more. We'll have as an outcome of optimization eigenvalues that are more to the left of the damping threshold. The only risk is that might have maybe in some conditions that are not contemplated in the design, so eigenvalues that are close to the lower part, and that might be a very low frequency mode that might be poorly damped. And with the lower the frequency, the more difficult to damp it quickly or more effectively in a system. This is also a dangerous situation. This is a fan-shaped region. So some authors defined like 4 or 5 years ago, 6 years ago, another nice approximation. This looks a bit like this damping threshold, but the trick of this one is that they have shifted the damping ratio line from the region to a decided real part, decided rate of decay. With this trick, then you prevent both problems, risk of some unexpected low frequency, poorly damped low frequency oscillations or poorly damped high frequency oscillations. That theoretically should solve the problem. So then the eigenvalue is just shifted by the thresholds, and then we compute the difference, and the rest is okay. But that will be a good format to try in case you would like to avoid some unexpected poorly damped oscillations that, for instance, because of not contemplating a given loading condition or given disturbance might be overlooked in the design. That's why it's always looked to test the stabilizer, for instance, in conditions that were not considered in the design to see whether you are having a successful damping oscillations or not. Is your optimization outcomes valid for all conditions, including unforeseen? This is something that you will always have to carefully check. The last thing is the wide area control. This means we might have this stabilizer, kind of stabilizer here, having any kind of input signals that I measure in the system, not only variables of generators like frequency, speed of acceleration, power, electrical power, but it could be anything. Could be the voltage angle of in a bus bar in a substation, or could be the current in a transmission line, or could be the frequency in a wind power plant, anything. And then this is the input of the stabilizer, and this might be located in any other device on top of the local stabilizer that could be added there. So we have here two big challenges in this, call it wide area damping control. One is selection of this input. So what PMU signal is the best for us input, and what is the best output, in which place I'm going to add this wide area controller. And second is robust performance. So I would like to have good damping in all possible conditions. So for the robust part is the optimization, what we already saw, how to tune it. And then for the selection of the control input and output is what we have to be careful, how to select. For that, as I told you, we need to look at the observability. This is a called geometric measure of observability. I have put a publication here that you can click on this in the PDF version of this presentation, and you will be directed to the accessible paper in which these formulas are explained in detail. But basically, we are here looking here at the dot product between the right eigenvector of a critical oscillation and an input element in the input matrix. So we have the dot product, and this is basically helping us to see the extent of effectiveness of adding an input as projected in the space of the oscillation change. Remember the right-hand vector, sorry, the C matrix is for the observability, how much we're going to observe for a given eigenvector. So it's the projection of the eigenvector and of this metric on the eigenvector. You remember the right-hand vector, the angles help us to determine the oscillation type. So this dot product is what helps us to have a more comprehensive measure, which we can use to rank signals to say we have good observability. The dynamics of this oscillation are confidently quantified with this factor here being higher value. We have something similar for controllability. In this case, we have the left eigenvector, and the element of the input matrix is also a dot product. And the higher the controllability measure, the better the signal would be to add a controller. If we say we add this, the reference signal of a voltage source converter, electric power channel, then this has when projected to the corresponding right left eigenvector, this will tell us that that location is the best to add the wide area damping controller, for instance. And then we can make a joint observability controllability measure by multiplying these two metrics, the geometric observability and the geometric controllability. And with that, we have the complete metric for a given loop. So a given input signal and a given output signal that will form the whole supplementary loop in wide area. We can have many possible loops. And with this equation 32, we can have whole values and we can rank to see what is the most effective. If we do it for a number of operating conditions, we can maybe build a box plot and see how this metric varies per loop. So with that, we can select, for instance, which signal to add and the wide area controller and where to locate it. This example in a generator is an idealization. So we will add another stabilizer that will be wide area damping control. We have to take into account a bit of a time delay because of the wide area communication, which will be probably some 100 to 200 milliseconds. And then where it's going to add, because this is going to influence the response, the modulation of this, look at the adjustment of, for instance, of the reference of the exciter. And then the optimization is as we already, for the robots, as we already explored in the previous slides. So that is basically more or less for today. If you have any question, please do it now.
Yes, it's time for question and answer. Initially, I would like to say thank you, Jose Luis, for taking time of your very busy agenda and and come here and deliver this very in deep detail lecture to the students. And now it's time for question. Let's see. Any one of my students here like to try a question? Please feel free. Don't be shy.